So, a matrix. Just so you know, we are doing two lessons today, two learning targets actually. One of them is super duper easy, like something you could have learned in like third grade. Second one, second one's tricky. I'll be honest. Usually like to say, hey, you'll get it. You will, but it can be confusing. All right. So we're going to work on what a matrix is and start out with the basics. And then we're going to learn how to just add and subtract these matrices, which is a piece of cake. But then multiplying matrices gets confusing, and we're going to spend most of the time on that. So let's get started with the easy target first, because it's bright and early. We're still getting used to the day and waking up. And let's talk about what is a matrix. And it is not this that some of you have already suggested. It is not Neo in the Matrix. It would be cool if we were jumping into this virtual computer program simulation that we call life, but that is not the case. No, a matrix is far simpler than all of this. It is just a collection of elements, typically numbers. That's what we're going to be working with for the most part. It's a collection of numbers that we call elements. They could be other things besides numbers. They could be expressions or equations or whatever. And they're just arranged in specific rows and columns, kind of like a grid, but this grid can be any size. We represent a matrix with those square brackets around the entire grouping, the entire grid. So here are two such matrices. Again, matrices is just the plural of matrix. So right here, this we'd call matrix A. We always represent matrices with capital letters. So capital A equals, and then these square brackets let us know, hey, this is a matrix, and there's four elements in there, those four numbers, 2, 6, -3, and 1. So that's one matrix. Here's a different matrix, matrix M. Again, a capital letter. And this one, it's just a single row, but there are three elements, a -2, an 8, and a 5. So it's just a collection of numbers. We represent these with a capital letter. So we're going to be seeing a lot of these. In this first lesson, 3.1, this is your next learning target, being able to add and subtract matrices. Again, this will be a piece of cake for you, I promise. But first, we're going to go over a few basics of these matrices because it's something brand new for pretty much everyone. All right, so let's take a look. A certain property of a matrix is the order of it. And I want you to make a note, the order, or sometimes you'll hear it called the dimensions. The dimensions of a matrix, it's basically the size of it. It's the number of rows followed by the number of columns. And so this first matrix A, the order of this matrix is 2 by 2, meaning there are 2 rows and 2 columns. The order of matrix M is 1 by 3. There's 1 row and 3 columns. Now, oftentimes students confuse, what's a row and what's a column. The way that I always keep it straight, that helps me, is when I think of rows, I think of like going into a movie theater, an auditorium, and there are rows of seats. Aren't they always sideways? Like the rows go left to right. So same thing on a matrix. The rows go left to right. That's how many like horizontal groupings there are. So there's 2 rows in matrix A. there's only one row, one horizontal grouping in matrix M. Then we've got the number of columns. Now, when I think of the word columns, for some reason, I always think back to like ancient Rome or Greece, and there's big towers with like columns holding up the ceilings or outside of the pillar, and columns are these big, giant, vertical pillars, that support roofs. So I think, oh, like this is a giant column right there. Here's another column holding up the roof to my matrix. And so I always think of columns as being the up and down groupings. It's like the physical columns of numbers. Even here, these are also 3 separate columns, even though there's just one number. They're mini columns, it's like a little roof. So you can just draw the rest of the roof if you want, right? It's still early, huh? Maybe there's a clock tower in there. There we go. Now it's a tower. You're all smiling under your masks, right? Good. And so the columns, that's the second number. So matrix A has 2 columns. Matrix M has 3 columns, 3 vertical groupings. And whenever we list the order of a matrix or the dimensions of the matrix, we always list the rows first and the columns second. And the way I always keep that straight is when we think about an ordered pair, like a number, like a coordinate on the coordinate plane, isn't x first? That's like the horizontal distance. That's the left and right. Then y is the second number, the vertical distance, the up and down. And so that's like how many columns, how many up and downs. And so I think always rows first, and then columns second, like x are the horizontal rows, and then y are the vertical columns. And the order that you list rows and columns is very important for our second lesson. We need to make sure that we've got that order correct. The order of the order. All right. Order. Okay. All right, here we go. Wow. So here's matrix A. It's huge. And I guess you don't need to write all this down. I'd like you to this should make common sense to you. I just want to use this to illustrate. So here's matrix A on the left, and it has 9 elements into it, right? It's a 3x3 grid. Sometimes we want to pick out a specific element from the matrix, at this specific location. And so each element in a matrix has like an address. And the way we would label this address or this location is by writing the letter of the matrix, so matrix A, and then this little subscript, which is always going to be 2 numbers. That's not one number, that's 2 separate numbers, right? It's not 23, that's a 2 and a 3. And that 2 and 3 simply represent which row and which column I'm referring to. So when I write A23, that means go to matrix A. All right, so I'm in matrix A. Go to row 2. Well, this is row 1. This is row 2, right? And then I want that second number is a 3. That's column 3. So here's column 1. Here's column 2. Here's column 3. So I want the element at row 2, column 3. That would be right there, that 0 in the middle row on the far right, because that's row 2, column 3. So my shortcut abbreviation for the element would be A sub 23. Down here, the second example, A31, that's not 31, that's row 3, column 1. So I'd go down, here's row 1, here's row 2, here's row 3. So I'm in row 3, but I want column 1. That's that first column. So I'm looking right here in this spot. There's A, row 3, column 1. And in matrix A, that'd be a 6. That's the lower left corner in this example. And so this matrix on the right is just kind of illustrating how everything is named. Notice how everything in row 1 has a 1 as the first digit, right? Because that's row 1. Everything in row 2 has a 2 in front because that's row 2. And then row 3 all has a 3 as the first digit. For the columns, you look at the second number, right? Column 1, column 2, column 3. Then in row 2, it's column 1, column 2, column 3, and row 3, column 1, column 2, and column 3. All right, so it's just a short abbreviation for the location of elements in the matrix. We good with this so far? Awesome. Okay, so just to practice, I want you to identify these 4 elements down here at the bottom. So B11, C11, C23, and C32. I want you to identify those 4 elements right now in your notebook based on matrix B and C, which you see in the top right. Just practice the whole row and column concept. I'll give you a minute. Okay, let's take a look at each of these. First off, B11. So that's matrix B, row 1, column 1. So that's the very first element in the matrix. So this is row 1, and this is column 1. And so I'm really looking at just this first element, which is going to be a 6, right? First row, first column, that first element is a 6. So B11 is a 6. For C11, that should be the same position of the C matrix. So I'm going over to the C matrix, row 1, column 1. So the very first element in that matrix is a 1. So you should have a 1 there. And then we've got C, row 2, column 3. So here's row 1, here's row 2, and then column 3. Well, if this is row 1, this is row 2, column 3 would be like over here. But is there anything in column 3? Do we have anything there? No, there's nothing. This doesn't exist. So you can just say, hey, this is undefined, does not exist. There is no C23. Doesn't exist. It's undefined. What about C32? Does that exist? Yeah, we've got a row 3 down here, column 2, that's a 6, right? How many of you had that last one? Beautiful. Excellent. All right, how are we doing identifying elements of a matrix? Pretty easy peasy? Good. All right, so now to the actual operations piece, adding and subtracting the matrices. Don't worry, this is still pretty easy. First, just one quick note. If I'm going to add 2 matrices together or subtract them, there's one criteria that needs to be true before we can actually follow through with the addition or subtraction. And that's written right here in bold. So I want you to definitely write down just this first piece right here. The matrices need to have the same order, right? The dimensions, like the rows and columns. So if you want to put in parentheses, they basically need to be the same size. They have to have the same number of the rows and the same number of columns. Otherwise, I'd be trying to add an element in one matrix with something that doesn't exist in the other matrix, right? They each have to have like a corresponding position or address in both matrices. So before you even add or subtract, check to make sure they're the same size. Once they are the same size, then all you do is go through like every address position and add up the corresponding elements. So like the first element in one matrix gets added with the first element in the second matrix, and that becomes the new position 1, 1. And you go through and do that for every single location in each row and the columns. You go through one row at a time, each column. Your resultant matrix, or just your result, that's like your new matrix that you're going to create once you add them up, it should have the exact same dimensions. It should be of the same order because you're adding up the same number of elements in each matrix. So you're adding corresponding elements. Basically, you're just matching the positions or matching the locations. Match the locations. So row 2, column 1 in one matrix gets added with row 2, column 1 of the second matrix. You add them up, and that goes into row 2, column 1 of this new matrix that you're creating together. So here's our first addition example. Go ahead and write these two matrices down. By the way, whenever we read off the elements in a matrix, we always do it one row at a time. Do the entire first row, then read the entire second row. So this first matrix contains the elements 4, -1, 0. Then on the next row, 8, 6, -3. And we're going to add the second matrix with the elements 12, -16, -1. And then in the second row is a -8, 5, and 6. So first off, before we actually try to do any adding or subtracting, can we add and subtract these matrices? Do they have the same order? Same rows, same columns, right? They're both 2 by 3s. 2 rows, 3 columns, plus 2 rows, 3 columns. Perfect. So we can add them together. Now all we do is match up elements. So I'm going to have a new matrix that will also be a 2 by 3. It'll have the exact same dimensions as the two that we're adding together. I take the first element in one matrix, I add it with the first element in the second matrix. 4 plus 12, we get 16. So then 16 goes into that same location in our new matrix, or our resultant matrix, which just means result, the answer. Then moving along in the row, stay in that same first row, and now we're going to add the second element, which is a -1, with the second element in the second matrix, which is a -16. So -1 plus -16 gives us a -17, and that sum becomes the second element in our result matrix. And we keep on going through with this pattern. Moving along the row, the third element plus the third element, that's a 0, plus a -1, that gives us a -1. Now once you get to the end of a row, just drop down to the next row, starting over from the front. So here I've got an 8 plus a -8. I add those up, I get a 0. And this is going to go in the second row because we move down to the second row in our two initial matrices. 6 plus 5 gives us 11. And then finally, a -3 plus 6 gives us 3. And that beautiful cornucopia of colors in the bottom of my screen is the resultant matrix. It's what you get from adding the two together. What do you think? Is this the easiest lesson ever? It's a pretty basic concept, right? Adding. Subtracting, same idea. Just subtract each of the second elements. All right? So I want you to go ahead and try this one on your own. Just note, however, that this is a subtraction. And so I even put a note up there, be careful with the negatives, because what happens when you subtract a negative number? It switches to a plus, okay? And that's usually the one thing that trips up students like on the tests with these. So go ahead and subtract these two matrices from each other. All right, I like what I'm seeing so far. All right, let's take a look at subtraction. Make sure we kept everything straight. So I guess first off, can we subtract these two matrices? Do they have the same numbers of rows and columns? Yes, they do. These are both 2 by 3 matrices. And so we know that our resultant matrix will also be a 2 by 3 matrix, exact same order. And this is a 4, not plus 12, but a 4 minus 12 because of that subtraction sign. So 4 minus 12 would give us a negative 8. And that goes in that first spot there. Negative 1 minus a negative 16. All right, so here's where you got to be careful. You're subtracting a negative 16, which is just like adding 16. So it's actually a negative 1 plus 16, which gives you a positive 15. So that's where you got to be careful. 0 minus a negative 1, that's like 0 plus 1, which just gives you a 1. It's the weirdest one I've ever drawn. There, that's like the best one I've ever drawn now. Once you finish one row, drop down to the second row and start over. 8 minus a negative 8, that's like 8 plus 8, that'll give us 16. Then we've got a 6 minus 5. 6 minus 5 is 1. And finally, a negative 3 minus 6. Negative 3 minus 6 gives us a negative 9. Who had all 6 of those correct and kept your negatives straight? Woohoo! That's awesome. Good job. And that's it for addition and subtraction. Best lesson ever, right? Piece of cake. All right, go ahead and try this next one. Make sure you've got it. Go ahead and add them up. Wait a minute. Some of you aren't writing. Why not? What's wrong with these two matrices? These two matrices aren't the same size, are they? So do I just take like this column and I add it here and then I add it there? Is that what we should do with matrices? No, that is not what you do. So the dimensions or the order of each matrix has to be exactly the same. This matrix here on the left, this is a 3 by 1 matrix because it's got 3 rows and 1 column. Over here, this is a 3 by 2 matrix. It's got 3 rows again, but there are 2 columns. Those dimensions don't match. They're not the same size. So can I add this? No. So you can write there's no solution, or the solution is undefined. You can't add them up. I don't know what you get when you add those together. Technically, we should say it's undefined. Usually we use no solution whenever you're solving an actual equation, like for x or something. We're not solving it. It's just saying, hey, what do you get when you add this plus that? So we should say, hey, the sum of those two matrices is undefined, because you can't do it. You don't get anything when you add them together. But it's the same idea as no solution. I wouldn't mark off wrong on a test if you put the no solution symbol. I'd be okay with that for now. So we can't add them together, different dimensions. All right, lastly, we can add and subtract multiple matrices at a time, as long as they all have the same dimensions, right? Do these all have the same dimensions? Yes, they do. So I'd like you to perform these calculations. Just like if I gave you a math problem, hey, what's 6 minus 2 plus 8? Like, you could calculate that, right? You just go in order from left to right. Same idea here. Just go left to right with your operations. So like combine the first two matrices into one matrix, and then use that with that third matrix. I want to see what you get. Just go ahead and practice this. Give you another minute or two. So I'm going to combine these first two matrices together. And note that it is subtraction. And you just subtract the corresponding elements, right? First with the first, second with the second, and so forth. So 1 minus 5 is negative 4. 2 minus 6 is negative 4. 3 minus 7 is a negative 4. Any guesses for the last element? 4 minus 8 is also negative 4. Isn't that fun? So that was the combination of these first two matrices. So I performed that operation. First, I still need to add in this third matrix. So I'm now going to write the negative 9, negative 8, 7, and 6. So once I took care of the subtraction, now we just add these two matrices together, and we're done. Okay, so adding these, same idea. They're both 2 by 2 matrices. So yes, we can add them together. There is a defined solution. And add up corresponding elements. Doesn't really matter here since those are all negative 4s in that first matrix. And so we're going to get a negative 13, a negative 12, a 3, and a 2. Did anyone else get that matrix that I've got in purple? That's terrific. All right, and that's adding and subtracting matrices. Pretty sure it's my last slide. Okay, any questions on addition and subtraction with these new fancy matrices? Was it an easy lesson, like I promised? Right, pretty simple concept. So you are gonna have one assignment on Delta Math with just addition and subtraction, and like identifying the dimensions or the order of a matrix, or identifying single elements like those first two examples, super easy. And then some adding and subtracting. Piece of cake, right? We have an hour of class time left, and that's going to be for our second lesson, which is going to be a bit more complex. It's multiplication. Unfortunately, it's not as simple as just multiplying corresponding elements together like we did here with addition and subtraction. So maybe if you want to stand up, do some jumping jacks in place, crack your neck, crack your knuckles, get ready, because it's going to get tricky. But I think we can do it. All right. Multiplying matrices. So this is learning target 3.2. And we are going to learn two different types of multiplication. This first one on this page is a very basic concept. It's called scalar multiplication. And a scalar just means a single number by itself. And so in this first example, this 2 would be considered a scalar quantity. You see how that 2 is written in front of the matrix? It's like outside of it. Simply think of that as being a number outside of a parentheses in like a bigger expression. And you know how you'd like distribute that 2 like inside the parentheses? This is the same idea. And so if I've got this 2 out in front, I can distribute it. Basically just multiply it to every element inside the matrix. And this is called scalar multiplication, because I'm multiplying a matrix by a single quantity as opposed to multiplying one matrix by another matrix. Which we'll get to a little bit later. And so when I distribute the 2, you see I've just got the 2, the 2, the 2, the 2, all right there. So I'm taking that 2 and I'm distributing it from in front of the matrix to inside the matrix. And every element in the matrix just gets multiplied by that number, by that scalar quantity. And then you get your result once you multiply them together. 2 times 1 is 2, 2 times 5 is 10, 2 times negative 6 is negative 12, and 2 times 4 is 8. And if we compare like this first matrix to this resultant matrix, you can see that that result matrix is just twice as big. All the elements are twice as big as that original matrix because I just multiplied everything by 2. And so this is called scalar multiplication, the easier of the two types of multiplication. So I'd like you all to perform scalar multiplication right here with this example. So it's -3 times the matrix 0, -3, 8, 1, 5, 3. You're really just taking that -3 that's out in front and just distribute it inside that matrix times every element in each spot. Awesome. So my resultant matrix will have the same dimensions. It'll still be a 3 by 2. And just multiply each element by -3. So I'm going to take -3 times 0, which is 0. Then take -3 times -3, which is +9. Then go to the next row. -3 times 8 is -24. -3 times 1 is -3. -3 times 5, we get -15. And that last spot, -3 times 3 is a -9. How many of you had this matrix correct? Just to make sure we're all good. We're groovy. Scalar multiplication, piece of cake, right? No issues. Good, good. Ooh, that's a 1/4. What? We hate fractions. So multiplying by 1/4 is the same as just dividing by 4. So do the same thing, distribute this 1/4, but all you're really doing is essentially dividing every element by 4. So go ahead and try this one. Just make sure you're okay with fractions, because you'll see some of these on your Delta Math. And then, of course, simplify the fraction, right? All right, so if we just multiply by 1/4, that's the same as dividing by 4. We're going to get the same dimensions of the matrix. It'll be a 2 by 3. And 8 times 1/4 is 2. 24 times 1/4 is 6. It's a very fancy 6, because I'm a fancy guy. 1/4 times 40 would be 10. Then the second row, 1/4 of negative 16 would be negative 4. 1/4 of 0 is still 0. 0 divided by anything remains 0. And then 1/4 of negative 12 is negative 3. Any questions on multiplying by a scalar, whether it's an integer or a fraction? I think we're good. And then one more thing we can do is combine those operations, right? So this is addition and scalar multiplication. See how I've got a 3 out in front of that second matrix? So we're going to be able to perform operations with matrices, just like we do with regular equations. And whenever we're performing these simplifications of these matrix math problems, we still are going to follow the correct order of operations, your PEMDAS. And so I've got two operations here. This 3 is being multiplied by that second matrix, that scalar multiplication. But I also have addition. And so according to PEMDAS, which should come first, the multiplication or the addition? Anyone can answer. Thank you. So we're going to multiply first. So let's figure out, what does this equal? Go ahead and distribute that 3 to each element first. Then you would add those two matrices together. So when I write this, I'm going to leave that first matrix the same. -8, -2, -6, and -3. So that matrix stays put, and let's go ahead and do the scalar multiplication on the right. And just distribute that 3 to each element. 3 times 5 is 15. 3 times 4 is 12. 3 times 8 is 24. And 3 times 6 is 18. So that second matrix now changes to that. Now it's a basic matrix addition problem. Just add those corresponding elements, and you're done. And they are the same dimensions, so we know we can add them. This sum is defined. -8 plus 15 is 7. -2 plus 12 is 10. -6 plus 24 is 18. And -3 plus 18 is 15. And this right here would be the solution. Questions yet? We good so far? Not too bad, right? Okay, just baby steps. I'm not going to have you do this one. It's just showing you can have multiple things. I think you all can distribute and add and subtract just fine at this point. All right. Now to the main part of today's lesson, multiplying two matrices together. All right, so definitely wake up for this part. Here's where the challenge begins. We're going to multiply one matrix times a second matrix. And in order to do that, it's a little different than addition and subtraction. There's still like a check at the beginning to make sure, can I actually multiply these together? And what you need to do is make sure that these inner dimensions match. And here's what I'm talking about when I say inner dimensions. I've got two different examples here. All right, and on the left, I'm going to write the dimensions of each matrix just right below it, right? The order of it, the rows and columns. This first matrix with the 8 and 9, that has one row and two columns. So that's a 1 by 2 matrix. This second matrix, the 3 and the 4, that has two rows and 1 column, right? That's a 2 by 1 matrix. Now, when I write these out underneath it, and this is exactly what I want you to do also, write the dimensions or the order underneath each matrix. You're checking these inner dimensions. See how there's like 4 numbers written across? There's 2 numbers that are in the middle. Those numbers in the middle have to be the same in order to be able to even begin multiplication. Essentially what it's saying is the number of columns in the first matrix has to match the number of rows in the second matrix. But I think it's a lot easier just to check, say, hey, do those inner dimensions match? On the right, this first matrix, this giant one, has 4 rows and 3 columns. That's a 4 by 3 matrix, 4 rows, 3 columns. This second matrix has 3 rows and 2 columns. It's a 3 by 2 matrix. Can I multiply those second 2 matrices together? Do those inner dimensions match? Yes. If we look here, the 2 numbers in the middle are the same. Doesn't matter about those outside numbers, those outer dimensions, just those inner ones must be the same in order to multiply. If those numbers were different, you would stop right there and just say undefined, right? When I can't multiply these together, or the product of these 2 matrices is undefined, we're unable to perform that calculation. All right, so just make sure you understand that before you multiply, write out those dimensions, the order of each matrix, and those inner dimensions must be the same. So we're going to practice. I've got 4 different matrices here. D, and just write yes or no. Or write out the dimensions of each of these. So write matrix A, and then write the dimensions of each of those 2 matrices, and then tell me, can I multiply them, yes or no? Then write down B, write the dimensions of each of those matrices, and then tell me, can I multiply them, yes or no? So I'd like you to do that for all 4 of these. Write out the dimensions or the order of each matrix being multiplied together. And then I want you to do that check, right, with those inner dimensions. Can I actually multiply these together? All right, so A, B, C, D. Just give me a yes or no for each of them. Nice. Write it in your brain. All right. So for A, these dimensions, say 3 by 2 times another 3 by 2. Hey, the dimensions match. That's good, right? Can I multiply these 2 matrices together? No, because those inner dimensions don't match, right? This is a 2, and that's a 3. So we cannot multiply those first two matrices together. We could add them or subtract them, but not multiply. How about B? Does B work? So let's see. This first matrix, that's got 3 rows and 2 columns. That's a 3 by 2 matrix. This second matrix has 2 rows and 1 column. Do those inner dimensions match? Yeah, can I multiply them together? Yes. So right here, those inner dimensions are the same, so we're good. B can be multiplied together. Down in C, well, this is a 2 by 2 and a 2 by 2, and there everything's the same number, so yes, we can definitely multiply the matrices in C together. And what about for D? We've got 1 row and 4 columns, right? 1 horizontal grouping and 4 vertical groupings. It's a 1 by 4. The second matrix has 4 rows and 3 columns. Do those inner dimensions match? Can I multiply them together? Yep. They've got a 4 and a 4. So yes. So it was no, yes, yes, yes for multiplying. Okay, so that's the check that you have to do before you even begin. Can I multiply them? If no, you just write undefined and you're done. If yes, however, well, here we go. So, write this down because it's kind of weird. The way multiplication with matrices works is you take each element in one row and you multiply it by each element in the other matrix column. Then you add those together. And I'm going to walk you through this, but just write this down so you've got it in your notebook. We're multiplying each element in each row of the first matrix, which each corresponding element in the column of the second matrix. So essentially, this is the first element in this row with the first element in that column. They would get multiplied together right here, 1 times 5. Then I take the second element in that row times the second element in that column. And I multiply those together right there. Once I've gotten to the end of my row or my column, then we stop and we add all those together. So that's that 5 plus 14, and we get an answer of a 19. So 19 is now just the first element in my solution matrix. And we're going to do every combination. You're going to take one row times each column, then take the second row times each column. And I'm going to walk you through this process on the next slide. So just have that statement written down in your notes. And then I'm going to go through and walk you through this example one step at a time to help you visualize this, to see what's really going on. And so this 19 isn't the entire product, that's just the first element in my solution matrix. So multiply everything and we always use the rows in the first column, and we always use the rows of the first matrix, and we always use the columns of the second matrix. And again, I always keep that straight, just because that's the same thing as like X and Y, right? X is horizontal, comes first, Y is second, vertical. So I use the horizontal things of the first matrix and the vertical things in the second matrix. X before Y, horizontal before vertical. So let's break this down one element at a time. On the far right, that's going to be our solution matrix. And we're going to have 4 numbers in there. And this is just how we find that first number, that first element. And you can see I've got them circled right here. So we're taking that first row times the first column, and I'm matching up the corresponding elements. meaning the first element here gets multiplied with the first element there. So that's a 1 times a 5, which gives us 5. Then move on to the second element in each of those groupings. Second element in that row with the second element in that column. They get multiplied together also. That's 2 times 7 right here. That's a 14. Now that I'm at the end of the row, then we just add those all together and we get 19. And that becomes the first element in our new matrix. Now, we always move across remember the way that I read elements in a matrix? We do one row at a time. Do the entire first row, then the entire second row. So I'm starting by using the first row. In my second matrix, I use my first column. Now I'm going to move over to the second column. So take a look here. For my second element, notice I'm using that same first row, the 1 and 2. But now, in my second matrix, I've already multiplied that row times the first column. So now I'm taking that first row times the second column, doing the same process where you're multiplying corresponding elements together. The first element in the row gets multiplied with the first element in the column. That's a 1 times 6, which equals 6. And then move on to the second element in each of those groupings. Move on to the second element in that row, gets multiplied with the second element in the column. That's a 2 times 8, which is 16. You now add all those products together, and you get 22. And that's the second element in our matrix. Now, if there were a third column, I would do that same process. I would then move on to the third column, still using the first row. So you always start with the first row, and you stay with that first row until you multiply it by every single column. Once you get to the end, once there are no more columns, then you're going to go back to the beginning, and now you're going to drop down to the second row and start all over again. So now that we don't have any more columns, I'm going to go back to my rows, and look at this. Now I drop down to the second row, which is this 3, 4, and I'm multiplying it by the first column. So it's like I'm multiplying every combination of each row with each column. So we're multiplying these corresponding elements. So the first element in the row gets multiplied with the first element in the column. 3 times 5, which is 15. Then we take the second element in the row with the second element in the column. That's a 4 times 7, which equals 28. We now add those together, and we've got a 43. And that is our next element. Now notice in our solution matrix, instead of writing the numbers across to the right, I've now jumped down to the second row. Basically, whichever row you're multiplying with, that's the row that you're going to be in your solution matrix or in your resultant matrix. And the way that it turns out is like the address of each piece. Like if I look at this 43, its address would be row 2, column 1. Remember that like address thing looks like a 21, row 2, column 1. And if you look at what we are multiplying together to get that element, look at this. This is row 2, column 1. So whichever row and column you're multiplying together, that is the location of that number in your solution matrix. So then that 43 is in row 2, column 1. That's where this will be located. Whichever row you're using in your first matrix is the row in your resultant matrix. Whichever column you're using that's going to be the same column of your solution matrix. And the same thing here at the end. We've got the second row times the second column. So row 2, column 2, and look at where our answer is located. Row 2, column 2. Right? That's how you know where to place it in your final matrix, in your resultant matrix. And it's the same process. You're multiplying the corresponding elements. So I've got a 3 times 6, right? The first element in the row times the first element in the column. 3 times 6, which is 18. Then the second element in the row times the second element in the column. 4 times 8. That's 32. Add those up, and you get a 50. And that's the final value in row 2, column 2 of our resultant matrix. Isn't that the weirdest thing you've ever seen with math up to this point? Come on, it's pretty crazy. What's crazier, Kramer's rule? No. Yeah, Ellie. Oh, of course. Is that okay? You're welcome. Yeah, definitely write this down. Add your own additional notes to help you understand this process, because it is very different. Row times column. And you're multiplying the individual elements, but then you're adding those products together to get a single number in your resultant matrix. So I'll give you a minute to finish jotting these down. I want to make sure that you've got everything written out clearly in your notes so that you understand this process. Then, of course, we're going to practice it. But this is it. This is the last piece of multiplying matrices, so we're just going to practice this for the rest of class. I think we can master this in half an hour. We got this. Any questions from anyone at home before we move on? Okay. So let's try one of these together. So for example, 5 for the multiplication lesson. Go ahead and write these two matrices down, and we're going to work through it together as a group. So the first matrix has the elements 5, 6, 7, 8. It's a 2 by 2 matrix. Our second matrix, also a 2 by 2, has the elements 1, 2, 3, 4. Let's go ahead and write these down. And then we're going to multiply them together. First off, can we multiply these two matrices together? Do those inner dimensions match? Yeah, they'd be 2s. This is a 2 by 2. That second one is a 2 by 2. And so these inner dimensions right there, do a quick check. Yep, they're the same number. So yes, I can multiply them. Now let's go through that process. Here we go. We always do rows times columns. Always X, I always think horizontal first and vertical second. So the first row times the first column. We're going to multiply these together. And the way that we do that is we multiply the corresponding elements. So the first element of the first matrix is a 5 times 1, right? That's this 5 times 1, which is right there, plus, then I'm going to multiply the second elements together, which is a 6 times a 3, plus 6 times 3. Okay, so 5 times 1 plus 6 times 3. 5 times 1 is 5. 6 times 3 is 18. And when we add those up, we get the number 23. So that's going to be the first element in our solution matrix. Now, I'm going to take this first row again, but I'm going to now multiply it by the second column. Okay, still the first row, but move to the next column. We keep on moving columns over until we get to the end. So now I've got 5 times 2, which is 10, plus multiply the second elements together. That's a 6 times 4, that's 24. And then we just add those two numbers together, and that's 34. All right, so we took the first row and multiplied it by each of those two columns. Now that we're out of columns, right, I've reached the end. There are no more columns past this. Now I'll go back to that first matrix, and we're going to drop down to the next row. So now I've got this second row, and we're going to start over with the columns. We're going to go back to column 1. So now it's the second row times the first column. Multiply corresponding elements, meaning the first with the first. So that's a 7 times 1, which is just 7. Then multiply the second with the second element with the second element. That's an 8 times 3, which is 24. And we're just adding these together. 7 plus 24 gives us 31. Now we have to take that second row times the second column. So row 2 times column 2. Multiply corresponding elements. So the first times the first, that's a 7 times 2, which is 14, plus second element, which is an 8, times the second element, which is a 4. 8 times 4 is 32. Add those two numbers together. 14 plus 32 is 46. All right, there are no more rows, no more columns. We've done it all. Now we need to put all these numbers in our final matrix together. If you haven't done so already, as you are multiplying them. And the elements from the first row, so I always think, what are the ones that I got from row 1? So anything that multiplied with the 5 and the 6, those would be those first two numbers. That's the 23 and the 34. Then when I drop down to the second row for my multiplication, I'm moving down to the second row in my resultant matrix. So then that second row times the first column was a 31, and then the second row times the second column was a 46. And this right here is your resultant matrix. 23, 34, 31, 46. In a fancy schmancy 2x2 matrix. Crazy process, right? Do you at least understand the mechanics of it? Like I know it might not be locked in your brain, but do you see what we're doing when we're multiplying those corresponding elements at least. And again, with a little bit of practice, it'll be much more comfortable for you. But as long as you kind of see where I'm getting these numbers from, how I'm calculating them at this point is what I'm looking for. So it seems like most of you are doing okay with that. Any questions on anything from this problem? Or any confusion or any steps that any of you want me to go over again? Or anyone at home? They're perfect. They're masters of this. All right. So I'd like you to multiply these two matrices together now. First off, can we multiply them together? I'm getting some nods. This is, okay, so that's one row and 3 columns, right? A 1 by 3. That second matrix has 3 rows and 1 column. So the inner dimensions do match 3s. So we can multiply them. Now this does look really weird because when we multiply rows times columns. But look at this. There's only 1 row and only 1 column. We're going to multiply those together, and our answer is going to be just a single number. So go ahead. What do you get when you multiply these together, everybody? Oh, you worked it out already? Man, you're too smart. Slow down. So when we multiply these corresponding elements, the first times the first, 6 times 2, we get 12. Then move to the second element in the row and the second element in the column. That'd be a 7 times 1, which is 7. Then the third element times the third element, that's a 3 times 3. That's a 9. There are no more elements, so just add those 3 products together. 12 plus 7 is 19. 19 plus 9 is 28. And then we would move to the second, column, but there is no second column, right? We're done. So then you'd move to the second row, but again, there is no second row. So there's nothing else to do here. So our actual answer, look how weird this is. It's a 1 by 1 matrix. There's only one element in it, and it's just the number 28. It's crazy. Questions on this one? Just want to show you a strange example of it that can happen sometimes. Okay, example 7. First off, can we multiply these matrices together? Do the inner dimensions match? So write down the order of the first matrix and the order of the second matrix. This is a 3 by 2 matrix because there are 3 rows and 2 columns. The second matrix is a 2 by 2 because there are 2 rows and 2 columns. And if we check those inner dimensions, they do match. So yes, we can multiply them together. I'd like all of you right now to try to multiply these on your own with that whole row and column process. All right, it'll take you a few minutes. That's fine. So write these out and multiply these two matrices together. So remember, each row of the first matrix times each column of the second matrix. Look at those previous examples to help you out. Follow the process. Okay, let's take a look at this together. So we always multiply rows times columns. Always do that first. Do the first row and the first column. Always go horizontal and then vertical second. And I'm going to multiply these corresponding elements. So I've got a negative 1 times 9, which gives me a negative 9. Then move over to the second element in each row and column. That's a 3 times 1, which is 3. Add those together, and we get a negative 6. Now we're going to take that same row but we're going to move over to the second column. We're still just moving across our solution matrix. So if we do want to write our solutions here, so that first element is a -6. So that's the first element in our resultant matrix. Then I'm still in row 1, but I'm going to column number 2. We multiply those corresponding elements. -1 times 7 is -7, plus multiply the second elements together, and that's a 3 times 3, which is 9. Add those up and we get a 2. So then 2 is your second element in your resultant matrix. Now there are no more columns, so we know we're done. Now we're going to drop down to the second row and repeat the process. So I'm taking row 2 times column 1. Right, take that second row and you're going to multiply that second row times each column. 2 times 9 is 18. -2 times 1 is -2. Add those up and you get a 16. Now because we dropped down to the second row on my first matrix, make sure when you're writing your answers, your solution matrix, you also put this 16 now in the second row. You're starting over on the second row. Then take that second row times the second column. Multiply those corresponding elements. I've got a 2 times 7, which is 14. We're adding a -2 times 3, which is a -6. Add those up and you get 8. So that's the fourth element in our solution matrix. All right, we ran out of columns. So go back to the first matrix and drop down to the next row. We're now on row 3 of our first matrix. And so then we're going to move down to row 3 in our solution matrix as well. So I've got that third row times the first column again. 1 times 9 is 9, plus 4 times 1 is 4. Add those up to get 13. And notice I'm putting that 13 down in the third row of our resultant matrix. And then take that third row times the second column. 1 times 7 is 7, plus 4 times 3, which is 12. Add those up, you get 19. And 19 then is the final element of our solution matrix. Did anyone get that correct? Just out of curiosity. Wonderful. That is awesome. Super excited. So yeah, that is your resultant matrix. That's so great that all of you got that. There's a lot of steps in there that you can easily trip up on. So it's great that you kept it straight. Any questions on this before I move on? Anyone here or anyone at home? Was there a step that you were confused on, or how I knew like where each number belongs in our solution matrix or anything like that? Awesome. Wow, you're doing great, everybody. I'm impressed. So one thing I want you to know, you don't need to write this down, okay? Just take a look up here, something that you may have observed. Whenever we multiplied these matrices, these are the same 3 examples we just did, so you don't need to write them again. But if we looked at the dimensions of these, oops. So like this first one was a 2 by 2 times a 2 by 2 matrix. And remember how we had to check to see if the inner dimensions matched in order to multiply them? Well, those outer dimensions also have a use. It turns out that whatever these outer dimensions are, those will be the dimensions of your solution matrix. All right, so it's just an extra little way to check or verify that you put all your elements in the solution matrix correctly. So like if I look at example 6, this was a 1 by 3 times a 3 by 1 matrix. And those inner dimensions matched. And look at the outer elements. It's a 1 and a 1. And didn't we get just a 1 by 1 matrix for the answer for this one? It was just that single number. It was a 1 by 1 matrix. And this last one that we just went through, so this is a 3 by 2 matrix times a 2 by 2 matrix. Inner dimensions matched. And look at the outer dimensions. Would be a 3 by 2. And if we go back and look at that final problem, check it out. We've got a 3 by 2 matrix here, right? This is a 3 by 2. So whenever you're doing that initial check to see if those inner dimensions match, can I actually multiply them together for each of these? It also might help you just observe what those outer dimensions are to let you know what the final matrix will look like. So if you do see ones here and you get only one number that says, hey, I should have just a 1 by 1 matrix, that's fine. We understand. It's going to look a little weird. Or a 3 by 2. So if you know, hey, how should I draw my my brackets, my square brackets to set up my answer matrix? Well, just know that it should be a 3 by 2, for example, 7. So just a little observation piece for you to recognize to kind of help you with the problems. Nothing I'm going to assess you on or anything, but just a fun fact, right? Who knew you're going to get a fun fact today? Okay. All right, so let's play a little game. I've got 4 matrices again. You do not need to write these all down. I simply want you to tell me what will be the order of each resultant matrix. What will be the dimensions of your solution matrix? So don't multiply these together. I just want you to write down in your notebook A, B, C, D. And I want you to tell me, without actually doing the multiplication, what kind of dimensions will your final matrix look like after you would multiply these together? Just to help you out, I'll write the order of each matrix down. All right, first off, can all 4 of these be multiplied together? Yes, the inner dimensions match for every one of these products. If we multiply them together, take a look at those outer dimensions. And so for A, the outer dimensions would be a 3 and a 2, so this would be a 3 by 2. For B, you would get a 3 by 1. For C, you're going to get a 2 by 4 matrix. And what are the dimensions of that last product for D? 4 by 4. That's going to be pretty big, right? 4 by 4. And I just want to show you the last thing with that matrix D. 4 by 4, that's going to be 16 elements you're going to have. It's going to be a big matrix. But look at how you'd actually multiply them together. It's pretty easy. Remember, you take one row times one column. There just happens to be only one element in each row and column. So I would just take 7 times 6, and that'd be the first element in the first grouping. Then I'd move to the second column, and that's going to be my second element. There's no that addition piece each time, right? So this would be column 1, column 2, column 3, column 4, just multiplying 7 times each of those numbers individually. Nice and simple. And then one last piece. Sometimes you're going to see problems like this. This is the last slide. if I represent matrices with capital letters, right, A and B, like I showed you way at the beginning of class, if I write something like 5A, that would mean take 5 times matrix A. You do that like scalar multiplication, right, and just distribute it. Or down here, where I have AB, that means take matrix A times matrix B, and then B times A. Would that be something different, do you think, if you switch the order of the matrices? You wouldn't expect that, would you? Ooh, we'll pick up there next time. All right, have a super duper day, everybody. It's been fun. You all did really well. You all made me proud. And I will see you around.